All right, one more example of applying algebraic manipulation to evaluate a limit. So let's look at the limit of the function 1 minus e to the negative x over e to the x minus 1. I wanted to do something here with exponential functions because I know they can be a little bit tricky working with them. So this example serves to remind us that negative exponents mean division, right? Like if there's a term with a negative exponent, then we can rewrite that term as a fraction, putting that term in the denominator and making the exponent positive. So I'm going to take this this part here, the e to the negative x, and I'm just going to rewrite that part of it with a positive exponent. 1 minus 1 over e to the x, and then over e to the x minus 1. Okay, so do we like this function is like a combination of other things, fractions and rational functions and e to the x's and all kinds of kind of messy stuff. But this here is actually a continuous function on its domain. So the question is it defined at 0? Well, what's e to the power 0? Here's where knowing your graphs is really essential. If you remember to watch the essential catalog of essential functions video that I put up there, I think I put it in the review. The catalog of essential functions goes over all of our basic functions, and you should know their graphs and some key features about them. So this is the graph of e to the x, y equals e to the x. And in particular, right here at this y-intercept here, that occurs at 1. So what is e to the power 0? It's 1, right? So if we attempted direct substitution, we'd have 1 minus 1 in the denominator. 0 in the denominator again. Most of these problems here, in fact, actually all the examples I've chosen have had 0 in the denominator, and that's the issue we're trying to work around. The 0 is also in the numerator again. 1 minus 1 over e to the 0 would be 1 over 1. That's 1. So 1 minus 1, yeah, that's also 0 up there. So we keep on having this 0 over 0 format, which we're trying to work with, manipulate it until it's not 0 over 0. So what can we do to simplify this? Again, like a previous example, it is like a compound fraction, so we have a fraction within our fractions. So let's take the denominator of that and multiply by that denominator, e to the x, up here. So we're going to do times e to the x. And then also down here, we had e to the x minus 1, and we're going to do times e to the x. So we're doing that to cancel out the denominator that we had over here. So the next step is to distribute up here in order to do that canceling. I'm not going to distribute the denominator. So in the numerator, though, we're going to get e to the x times 1, which is e to the x, and then minus e to the x times 1 over e to the x. Those will cancel, right? And just give me 1. Aha! Great. There we go. So now this factor, this whole factor, e to the x minus 1 will cancel out. Pow, pow. That theorem that says that as long as they're equivalent to each other at every point except 1 or 0, except x equals 0, then their limits were going to be equal. That theorem is kicking in right here, allowing us to do this. And now we can say, well, this is just a composition of two continuous functions, which is still continuous. So we're going to do 1 over e to the power 0, and that's, again, e to the power 0. Hopefully you have this picture in your brain, just embedded in there and easily recallable. So e to the power 0 is 1. You know that. Anything to the power 0 is 1. You don't need the picture to tell you that. But the picture is still handy. And we did it. We solved that limit. So I'm going to show you one more limit theorem, which is useful and a neat example of it. And then I think we're done for 2.3.